Okay, we're back to part 2 of decision field theory, and we're going to talk about a new topic this time. Last time we talked about decision making under risk or uncertainty. Oops, this kind of decision right here, we have maybe a risky option versus a safe option. There's different states of the world, and so we talked about how you make these decisions where you have to judge the probability of these different states of the world and evaluate the utilities of the actions. So that was what we did last time, but this time we're going to turn to consumer choice problem. So let's get to that slide here. Not that page here, down here. Okay, consumer choice decision making. So instead of trying to make decisions between risky or uncertain alternatives, now we're going to be trying to make decisions between what we call multi-alternative, multi-attribute alternatives, like consumer choices. So like a typical one is right here, choosing a car. When you're choosing a car, you have to evaluate things like the quality of the car, the economics of the car, and we might have different options like a BMW and a Honda and a Ford. Now, this is an oversimplified diagram right here. I mean, when you think about the quality of the car, of course, there's lots of things to think about for quality, like, what kind of seats do you have, and what kind of engine you have, and what kind of speed, and what kind of style of the car and color. All kinds of things go into quality. So we lump all those all those detailed aspects. They all go into an attribute called quality. Then there's another attribute, a major category called economics. Like the cost of the car, the miles per gallon. How much it costs to repair the car, insurance for the car, things like that goes into the economics. So there's lots of aspects and features of the economics to think about. So when you're making these decisions, your attention's kind of going back and forth. You're thinking about different quality aspects, then you start thinking about different economic aspects. And so that's what makes this decision hard, is how do you trade off the quality for the economics? Now, I got some scores in here. It's kind of like a consumer report score, but these are just kind of oversimplified just to kind of help illustrate how this theory works. But remember, like, quality is actually a whole bunch of different specific features, and economics a lot of specific features too. So whenever you think about quality, you might be picking up some high quality value from BMW, but if you think about quality, you might pick up some kind of low quality value for Ford. But if you're thinking about economics, just the opposite happens. You think about some low quality value for BMW because it's kind of expensive or insurance costs a lot. But then you'll think about if you think about economics, you'll pick up a higher score evaluation for Ford because you'll think, well, it's economical, the gas mileage is good, insurance won't be so high. And so, so these are the different kind of features that come into your mind when you're trying to make this decision, and you have to kind of weigh them and try to make your decision. And so we're going to apply decision field theory to these kind of problems. Now, so one of the interesting paradigms, well, this is not only interesting experimental paradigm, but also important for the industry, is when you try to introduce a new product on the market. So we're going to look at how introducing a new product on the market might affect your choice probabilities for earlier products in the market. So here we got what we call an attribute space. We have economics on the horizontal axis, and we have quality on the vertical axis. And so here's our BMW. It's high in quality but low in economics. And here's our Ford. It's low in quality but high in economics. And so we might have initially a choice between these two options right here. Or that maybe these are two cars that are already existing in the market. And then we're going to put a new brand in the market. And we're going to see what we're interested in, is what the effect of this new brand has on the choice probabilities for the original brands. If we put a new brand in here, is it going to hurt the BMW compared to the Ford? Or will it help the BMW compared to the Ford? So that's we're going to look at how this new brand shifts around the market share, essentially. So that's an important question for industry, but it's also an interesting experimental question. So the experiment, usually we study the choice probability between the two options first, and then we put a new option in, like here, we're going to call it X, and then we'll see how X affects, when you have a choice between all three, how does X affects the relative proportions for the original choice options. So let's take a look. And so we're going to review 30 years of research. And so these 30 years of research caused a real puzzle for traditional economic theories of choice, because these findings that I'm going to summarize rule out lots of economic models and seem to violate some kind of rational choice axioms. So we're going to look at something called the similarity effect that was investigated in the 1960s and 70s. And then later on, there was an attraction effect that was discovered in the 1980s by Hubert, Payne, and Puto. And then later on, Simonson discovered something called this compromise effect. And then later on, Tversky and Kahneman discovered something called a reference point effect. These are all reviewed, all this literature is reviewed in this article we have published in Journal of Economic Literature, 2006. So let's take a look at these effects. So here, this first effect we're going to look at is called the similarity effect. And we're going to look at what we call stylistic results, not the actual experimental findings. So the basic idea is, like, we first look at, let's say in a study, an experiment, we might first look at your choice probabilities between two options that we're going to just here label as the BMW and the Ford. These could be different records, like, a classical music piece and a jazz piece, something like that. But anyway, we have the BMW and the Ford here. So we first look at choice probabilities for the BMW and Ford, and we establish some kind of preference sorting, choice probabilities between these two. And let's suppose, just for sake of argument, well, let's say like the findings, that the BMW is chosen more frequently than the Ford in the binary choice. So that's fine. Maybe equality is more important. So let's say the choice probability is, let's say 0.6 for the BMW over the Ford. So BMW gets 0.6, Ford gets 0.4. Now we introduce another option right here, X. So now it's a choice between all three options. So it's a three-way triadic choice. Now X is designed specially, it's close to BMW. We reduce the quality a little bit, but we increase the economics a little bit, and so it's competitive. So it's competitive with BMW, but it's similar to BMW. And so what happens now? The question is, how does it rearrange these choice probabilities? And what we find in the similarity effect is now BMW is chosen less frequently than the Ford in the triadic choice. So when we have BMW, Ford, and this new option X, we find that the BMW is chosen less than the Ford. Ford becomes more popular. It's kind of like what happens is the similar option, when you introduce the similar option, it only steals from the BMW, leaves the Ford alone. So in a binary choice, maybe BMW is 0.6 and Ford was 0.4. But if you introduce X, now X competes with the BMW, so that 0.6 that was originally with the BMW is split between X and the BMW. So now it's 0.3, 0.3. So BMW is now 0.3, but Ford is 0.4, so we get this reversal. So that reversal is called a violation of independence. Because what we should find, the basic idea of utility theory, if BMW's got greater utility than Ford, established in a binary choice, if we introduce a common option X to the choice set for both choice sets, well, BMW still should be chosen more than the Ford because it's got a higher utility than Ford, and both sets have the common option X to compete with. And so we shouldn't get this reversal, but this reversal is called a violation of independence because the choice probability should be independent of this option X that we introduce. Now that violation of independence is an important property. Sometimes they call it the independence from irrelevant alternatives. Your preference ordering for Ford and BMW shouldn't be changed by introducing another independent alternative that's common between the two sets. But anyway, that violation right here, this reversal of the choice probability between binary and triadic, violates a lot of models, important models. So let's take a look at this slide here. Blow it up a little bit. Let's focus here on strong utility models. So a strong utility model says that, it's basically the idea of a strong utility model is we assign a utility to each option, and the probability that you choose an option, well, is determined by those utilities. So for example, the probability you choose the BMW out of the set BMW, Ford, and the new alternative X should be an increasing function of the utility for the BMW and a decreasing function of the utility for the Ford and a decreasing function of the utility for the competitive option X. So that's the strong utility model. Now that's a very general model, but that model cannot explain this violation of independence. It's ruled out by that model. An example of this model is the loose choice model. So loose choice model says the probability you choose the BMW would be the utility of the BMW divided by the sum of the utilities. And anyway, all of the models of this form imply the following inequalities. So in a binary choice, if the BMW is chosen over the Ford greater than 0.5, that means the utility for BMW must be greater than Ford. So then when we get to the triadic choice, well, this probability here is an increasing function of the BMW and decreasing function of the Ford. Well, the BMW is greater than the Ford. And it's a decreasing function of this utility X, but that's common. So we got this common X in here. And so it should only matter, so what should only matter in this comparison is the relative utilities of the BMW and the Ford. But now we find this is reversed. So this model requires these inequalities to remain the same, but the finding is that we find a reverse. So we rule out all of these strong utility models, including the popular loose choice model with the similarity effect. So now let's take another effect. This is the attraction effect. So this is going to demonstrate another important property. Okay, so we have our quality economic space again. And let's say in a binary choice, we got BMW and Ford. And let's say, suppose once again, like before, let's say the BMW is a little more popular, chosen more frequently. And so it's going to probably 0.6 of being chosen over the Ford. And now we introduce this new option X. Now X is designed to be similar to the BMW. So if you don't have a theory and you just kind of use phenomena, you might say, oh, this is the similarity effect. You know, if we introduce X, it's just going to hurt the BMW. It's going to leave the Ford alone. But no, that's not what happens. Now notice something special about this X. It's similar to BMW, but it's defective because, you know, you lower the quality, we're dropping the equality down, but we're getting no gain in economics. So it's not competitive. It's called defective. And so what happens is, you know, basically nobody should be choosing this option. There's no reason to choose it. But what they find is that now when you introduce this X and look at the triadic choices between all three, X boosts the probability from BMW. So in the binary choice, it was 0.6, but now in the triadic choice, let's say it goes up to 0.75. So X makes BMW look good, it makes it shine. I mean, logically, or, you know, in terms of rational choice, this should never be chosen. So this finding, so in the binary choice, BMW is chosen more frequently, let's say 0.6, but now in the triadic choice, BMW is even chosen even more often, let's say 0.75. So that violates something called regularity. Regularity says this can never happen. Regularity says that the binary choice of BMW over Ford, the probability of BMW should always be greater than the triadic choice of BMW, Ford, and the new option. The new option just should take away choices from BMW. I mean, it can take away from Ford too, but it must take away from BMW compared to, you know, just BMW and Ford competing with each other. Here, BMW's got to compete with all three. So the regularity says that this binary choice here should always be greater than this binary choice, this triadic choice here. But we're getting a reversal. The binary choice, no, sorry, we're not getting a reversal, we're getting a violation because the binary choice is smaller than the triadic choice. Let's say the binary choice is 0.6. This goes up to 0.75. So that's a violation of regularity. That's a kind of a violation we call a rational choice axiom. Adding this defective option somehow makes the BMW more popular when you should never even choose this option. Now this violation of regularity also rules out a large class of models. It rules out these random utility models. So what's a random utility model? The basic idea of random utility model is that it's like, unlike the strong utility model, assume you had a fixed utility you always carry around, and you make your choices probabilistically based upon this fixed utility. But the random utility model says, no, your utilities for options, they change from day to day or moment to moment, so they're randomly varying across time. But at any moment in time, let's say you've got a set of 3 utilities at that moment in time, and so you choose the maximum at that moment in time. And so the random utility model says, well, the probability you choose the BMW out of the set of all 3 is the probability that the utility, random utility for BMW happens to turn out to be the maximum of the utility for all 3. That's the probability that you'll choose it. The probability you'll choose it is the probability that this random utility for BMW turns out to be the maximum of all 3. And so we have to compute this probability for the model. The probability that B becomes maximum, that gives us the probability of this choice. Now the trouble with this random utility model, well, an example of this random utility model is the multivariate Thurstone or probit model. It's a multivariate normal distribution of random utilities. Or another example is McFadden's random utility model. They're both examples of random utility models. They're all ruled out by the violation of regularity. Now, why is regularity follow from random utility models? Well, because let's take a look at the probability that you choose the BMW out of all 3 for random utility model. Well, that would be the probability that the random utility for BMW beats the Ford times the probability that the BMW also beats the new option, given that it beat the Ford. So it's the product of these two. The probability that it beats all 3, probably all 3 is going to be the product of these 2. Well, this is the triadic choice right here. So the triadic choice is the product of 2 probabilities. The binary choice is right beneath it. And so this binary choice has to be greater than or equal to this triadic choice, because this product term, this other term in the product, is a number between 0 and 1. You know, if it's less than 1, then it's going to be less than the binary term here. So this can only reduce the probability. So the basic idea is if we introduce this competitor, you know, you're just introducing another option in the random mix that the BMW has to compete with, and so it's going to steal some of the choices from the BMW and reduce the probability. Well, the traction effect rules out all of those models. So that was a pretty important finding. So that's the second piece of the puzzle for economic theories of choice. Both the strong utility model and a random utility model were ruled out. Now the third part of the puzzle is the compromise effect. So this is an interesting kind of a finding here. Now let's go again. Let's take a look at the binary choices. Now let's focus on these 2 being the choice, like the binary choice. You get a choice between X and Ford. Like X is our Honda. Let's say you have a choice between the Honda and the Ford and the binary choice. Now let's suppose in this example, it's a little bit different, but let's suppose in this example, the Ford is preferred to the Honda. So the probability of choosing the Ford over the Honda is greater than 0.5. Probability of choosing Ford over the Honda is greater than the probability of choosing the Honda over the Ford. So this binary choice, people prefer the Ford. But now we're going to introduce this BMW to the choice set. Now notice, now we got 3 options: BMW, Exit, BMW, Honda, and Ford. What does the BMW do? It suddenly makes the Honda look like a compromise. You know, now BMW is at one extreme, it's high in quality, low in economics. Ford's on the other extreme, low in quality, high economics, and now Honda's right in the middle. It's kind of like this compromise. And so what we find is, in the binary choice, Ford was chosen over X, but in a triadic choice, with BMW making X look like a compromise, now X is chosen over the Ford. In fact, let's say maybe even chosen over the BMW. It becomes the most popular. In some of the studies, the compromise is the most popular. So that's the compromise effect. That's another violation of the independence property. So that violates the strong utility models. Now this compromise effect also violates, some heuristic models of choice, like the like to take the best, like Gigerenzer, Gerd Gigerenzer likes to use the take the best model. The take the best model, the way it works is, well, or sometimes we call it lexicographic model. Well, you focused on the most important attribute. Now let's suppose to you the most important attribute is BMW, and then you take the best alternative on the most important attribute. Well, that means you take the BMW. Well, maybe, you know, the most important attribute to you is not quality. Maybe the most important attribute is economics. So if you focus on economics, because that's the most important attribute, and then you pick the best alternative on the most important attribute, then you're going to pick the Ford. So you never pick the Honda. It's in the middle. It's not the best on any of these. So the compromise never turns out to be take the best, because it's not the best on any single dimension. It's a kind of a average best, which the take the best doesn't permit averages to be the best. So that's the third piece of the puzzle. Well, there's another one that's called the what's it called? The reference point effect. But let's stop with those three now before we run out of time here. So let's take a look at how decision field theory might explain these results. So anyway, for 30 years, they had all these results, and no economic model could explain all these results. So decision field theory, which is a sequential sampling model, it's a kind of a dynamic stochastic model, was the first to explain all these three results with one common set of assumptions, and even a common set of parameters could explain all three. Now let's see how decision field theory works for this. Now, first of all, you might recall when we first described decision field theory, we described it as this kind of a process. Like this is a choice between risky and safe alternatives. So we had two options, and you had a relative preference. So this is the relative preference for the risk versus the safe. So this is a difference between risk and safe. And so when you're going up, the difference is favoring risk, and when you go down, the preference is favoring safe. And as soon as you hit a boundary, you choose one. So in this case, you're thinking about, you know, this different states of the world, and you're accumulating evaluations of each option in each state of the world. And then here you're accumulating enough evaluations, thinking enough states of the world that favor the risk, and you choose the risk. So that was representing the binary choice with one single walk. But this one single walk is a difference between your relative preference between the two options. Now we're gonna build the same model here, but we're gonna represent it by two trajectories instead of one. And we're gonna do that because instead of using one trajectory like we have here, if we have two of them, it's easier to understand how to extend it to 3 or 4 or more options. So let's see how that works now. So here's decision field theory once again with just two options. So the basic idea is now you have a preference accumulator for the blue option, and you have a preference accumulator for the green option. Say if you're thinking about two motorcycles, thinking about the green motorcycle versus the blue motorcycle, you know. So, you know, here, when you start accumulating some evaluations, you know, maybe you initially start accumulating evaluations that favor the blue option against the, initially accumulate evaluations favor the green option over the blue option. But then you kind of switch and you start accumulating evaluations favoring the blue option over the green option. Now, what you might notice is in this space where we have two options, we're looking at the first option to hit the top boundary wins and determines the decision. So it's a race. It's a race between these two trajectories. And the first trajectory hit the top boundary wins and determines the decision. So here's when the blue one hit the threshold. And so that's when the decision is made. And you know, because the blue hit the threshold first, it's chosen. So, but this model is exactly the same as the previous one-dimensional model because these two this is a single preference state for the green, and this is a single preference state for the blue. They're perfectly negatively correlated. So as whenever the green goes up, the blue goes down. Whenever the blue goes up, the green goes down. And so only the difference is important. And so you could represent this two-dimensional process by a one-dimensional process, which would be just the difference between the two. So when the blue is much higher than the green, the difference is going to be very positive blue. But when the green is much higher than the blue, the difference is going to be negative for the blue and positive for the green. So you could represent these two alternatives in one dimension by just using the difference because they're negatively correlated. But now if we allow a separate accumulator for each option, it's easy to extend it to 3 options or 4 options. So here we have a red, blue, and a green option. Let's say, like our BMW or our Honda is the red and our Ford is the green. So now we have an accumulator for each option. So the BMW gets, we got a preference accumulating for the BMW. We got preferences accumulating for the Honda, and we get preferences accumulating for the Ford over time. So initially you start thinking of things that, let's say, favor the Honda. But then later on, maybe you start thinking of things that favor the BMW. And then you maybe continue thinking about those high quality things that favor the BMW. And so now it's a race between 3 options. The first of these 3 options hit the boundaries win, determines the choice. And so the BMW is chosen because it hit the boundary first. And the time it takes to hit that boundary determines the decision time. Of course, this example is in a second. If you're buying a real car, it would take days, but this could be going across days instead of seconds. But in a laboratory, it would maybe take 10 or 12 seconds to make a decision. But so the idea, though, is that here we want to look at differences again. We're really getting differences because what we're doing is we're requiring these preferences to sum to 0. So it's kind of a constraint. So when there's only 2 alternatives, they sum to 0, they're perfectly negatively correlated. When you have 3 alternatives and they sum to 0, they're negatively correlated, but not perfectly negatively correlated. The sum of the 3 sums to 0. So if one of them is going up, something's got to be going down. So in this case, the blue starts going up and the red starts going down a little bit, and then the green starts going down a lot more. Well, here, in this case, down here, you can see the blue's going up and the red's going up, but the green's going down a lot more. So they always sum to 0. So there's a competition still going on here, but it's no longer but now it's a competition among all 3. And so that's how decision field theory works with multiple alternatives. We put a separate accumulator for each alternative, but the preferences sum to 0. And when it reduces to 2 alternatives, summing to 0 means you only keep track of the difference, and so you can represent it by 1 dimension. But if you have more than 2 alternatives, then you need to keep separate trajectories for the separate alternatives. So let's see how this decision field theory works with multi-alternative and multi-attributes. So this matrix M, we call it the motivational values, M for motivational values. This M represents the values of each alternative in each attribute. Remember, started with this table. Now, of course, this table is oversimplified, but they're starting with this table. So this table becomes our M matrix. So the column is one of the attributes, like quality, or another attribute like economics. And the rows are different alternatives. And the cells represent the value of an alternative on an attribute. So that cell values the value of BMW on quality. And so, so the way we work this theory now is we have this multi-attribute, multi-alternative. The columns are the attributes and the rows are the alternatives. And so this is this M matrix. And so then we have a weight matrix, a weight vector. This weight vector is the amount of attention that you're putting on each attribute. Now we're assuming that your attention is kind of shifting over time. So you might focus your attention on quality for sometimes, and you'd be picking up evaluations on quality, which would favor the, say, the BMW. But your attention might shift later on time, and you might start focusing on economics, and then your attention is going to be focused on economics, and you're focused on the second attribute, and then you're going to be favoring the Ford. So this M matrix represents the values of each option on each attribute, and this weight vector represents the amount of attention that you're paying to the different attributes. Now the C matrix, is doing the comparing the alternatives. So like I said, these preference states, they have to sum to 0 all the time. That's what the C matrix is doing. So the C matrix is going to do, let's say it's going to be computing a relative preference for the BMW by comparing the BMW to the average of the Honda and the Ford. Then it's going to get the relative preference for the Honda by comparing the value of the Honda to the average of the BMW and the Ford. And then likewise, it's going to compare the Ford value to the average of the BMW and the Honda. So we get a relative preference by the C matrix. And now this gamma matrix here represents this growth decay factor we talked about earlier with the one-dimensional model. Earlier we talked about using this model in one dimension. This is a growth decay parameter. It can produce primacy and recency effects. We only need one single gamma in the one-dimensional model, which is keeping track of the differences between the two options. But in the multi-dimensional model, we need to replace that with a matrix. So that's what this matrix represents. So this matrix right here. Now this matrix, we call this the lateral inhibition matrix. Because what happens is the diagonal terms on this matrix are going to determine, rate of decay, like what's going to happen. Maybe it's helpful to jump down here. What's going to happen in this dynamic model is you're going to be accumulating preferences across time for all three options. And your new preference state's going to be, this feedback term here times your old preference state plus the new input. And so this feedback term here on the diagonal, it's got decay terms. So you're basically kind of summing up all these input valences that are coming in. You're summing them all up, but they're being weighted by, let's say, recency or primacy. And this gamma on the diagonal is going to produce let's say, recency weighting. If it's, let's say, let's say a number like 0.8 or something like that, minus 0.8 would give you a decaying of memory. And so that would give you recency weighting. So this is the feedback, that produces the memory for the previous state. So you get a memory for the previous BMW and a memory that's decaying for the Honda and so on. Now these off-diagonal terms, they represent what we call lateral inhibition. That's how one option starts to compete with another option. So if two options are really similar to each other, they produce more lateral inhibition. Let's suppose the Honda and the BMW are kind of similar because they're both, well, Honda's kind of a medium quality, medium price, so it's kind of similar to the BMW. And the Honda is also similar to the Ford because it's in the middle. But the Ford and the BMW are quite different, so there's no lateral inhibition connecting the Ford to the BMW. Only the similar options get connected by lateral inhibition. So this lateral inhibition produces kind of a winner-take-all accumulation effect. So that's what this gamma matrix does. This gamma matrix is very important for producing our context effects like attraction and compromise effects. So anyway, so the way model works is we define these matrices. This is a stochastic attention weighting vector that's changing from moment to moment. And these are the values of each option on each alternative. And these are comparing the alternatives, getting relative preferences. And then this is producing the lateral inhibition that makes a competition, and it kind of produces a winner-take-all effect. And so the valence that's coming in each moment in time is the product of these three matrices here. So if we just look at this first term, we got the M times the W, that matrix product. Like this is a 3x3 matrix times a 3x2 vector. This is a 3x2 matrix, 3x2 matrix times a 2x1 vector. What that's computing is like a weighted utility for each option, except that weighted utility is random. It's like a random weighted utility because the attention weights are randomly changing because your attention is kind of fluctuating from across the quality and economic attributes. So this product here gives you a weighted utility for each option. And then when we multiply it by the C matrix, we get the relative preference. So that computes the preference of, say, BMW compared to the average of the other two. And so that's the valence that's coming in. So that valence comes in. The C matrix makes the valence sum to 0. So it's called a contrast matrix that compares the options. So that valence is what's coming into this dynamic system. So this preference state now is a 3×1 vector. We get one coordinate for each option. We get a coordinate for first coordinate is BMW, second's for Honda, third coordinate is for the Ford. And so we do this feedback matrix times the old state plus the new input valence, and that gives the dynamics. So this dynamics is what's driving the accumulation of these preferences across time. So this P of T at each point in time is the position at each point in time. The increment at each point in time is produced by this valence. But P of T is integrating all these valences. So P of T is a position at any point in time. And so this dynamic right here is making that trajectory change across time. So we're getting this dynamic trajectory across time. And then when P of T hits the threshold for one of the options, that stops the process and that option wins. Now we can mathematically derive, some equations from this model. This model, when the time units get really, really small, becomes an Ornstein-Uhlenbeck multivariate drift diffusion model. And so we can derive some choice probabilities and distribution of response times mathematically from this process here, right here, this simple process. I'm not going to go through those derivations, but the model has a set of parameters. Actually, not many more parameters than a traditional random utility model. Actually, the only new parameters we introduced that go into this feedback matrix gamma. Otherwise, all the other parameters are shared by the random utility model. So we only add these extra parameters. So there is an extra parameter here, that lateral inhibition term, but that's the key parameter that you need for producing these context effects. So we can take this model and we can see, there's two critical parameters that we need for these context effects. That, one is the lateral inhibition. Right here, there's more lateral inhibition between the Honda and the BMW because they're more similar. There's more lateral inhibition between the Honda and the Ford because there's more similar. But there's little or no lateral inhibition between the Ford and the BMW because they're very different. So we can manipulate that lateral inhibition, which is key in the model. That's this parameter here. And we can manipulate the noise that comes into the stochastic diffusion process here. And then we can see for each one of these two critical parameters, can the model reproduce all three effects, the attraction effect, similarity effect, attraction effect, and compromise effect. And so these points here, these blue dots, show you that all the places where this multi-attribute, multi-alternative decision field theory, it reproduces all three effects using the same set of assumptions, the same set of parameters. Now it doesn't always, like over here, it might, let's say, if the lateral inhibition gets too low, you'll maybe get a similarity effect, but you won't get any attraction effect. If the lateral inhibition is high, but the noise is too high, you won't get a similarity effect. You'll just get a lateral inhibition effect, or you'll get a attraction effect. But in here in the middle, you'll get all three effects. So there's a broad range, where you can get all three. But this is also showing you that we predict that these effects should be negatively correlated, like the similarity effect, which requires low noise levels. The similarity effect requires low noise levels and doesn't require lateral inhibition. And so similarity effect, is strongest over here where the lateral inhibition is low and the noise is low. But the attraction effect and compromise effect are strongest over here. So, when you're getting a strong attraction effect, you're getting a weak similarity effect. And if you're getting a strong similarity effect, you're getting a weak attraction effect. So those effects are predicted to be normally, inversely correlated. Now these effects, we make a strong prediction with this model. So this is a dynamic model. And so we predict all these effects change across time. So this panel here is showing the predictions of the model for the similarity effect across time. So let's say this is deliberation time. Like, let's say you're increasing the threshold boundary so you sequentially sample for a longer period of time. So we're looking at how increasing your deliberation might increase the effects. Now, for this panel, to make it simple, we designed it so the binary choices were all 0.5. So, A was chosen over D with probability 0.5, A was chosen over C with probability 0.5, and C over D 0.5. So in a binary choice, they're all chosen equally often, 50% of the time. But now, in the similarity effect, what we're finding is is that the red option is similar to the blue option, and the green option is much different. And so what we find is when we introduce in the triadic choice, no, they're all 0.5 in the binary choice. They're all equal in the binary choice. But when we introduce this similar option red in the triadic choice, it hurts the blue option, and it leaves the green option intact. And so the green option becomes much more popular in the triadic choice, even though it was in a binary choice, the blue and the green were equally often chosen. But now introducing a similar option to the blue option hurts the blue option and leaves the green option intact. And so that's the prediction from this multi-alternative decision field theory. We predict the similarity effect. And it's through the attention switching mechanism, because what happens in the similarity effect, if you're paying attention to quality, let's say, so let's say this red option is similar to the Ford. Let's say it's a cheap car similar to the Ford. So when you're thinking about quality, only the BMW is going to win. But when you're thinking about economics, now the Ford's got to, share its share with the other competitive cheap option. So whenever you're thinking about economics, these two have to compete. But whenever you think about quality, only the BMW wins. So that's why we get a similarity effect by this attention switching. If you happen to be somebody that thinks about quality a lot, you'll pick the BMW. But if you happen to be somebody that thinks about economic a lot, you're going to be divided between these two economic options that are similar to each other. So that's similarity effect. Now this panel here shows the attraction effect. Now in this case, the blue and the green were in a binary choice were set to be equal to 0.5. But then we introduced this defective option, this red one. Now the red one is defective compared to the blue. So it's similar to the blue, but it's defective compared to the blue. Let's say, like before, let's say this blue one's the BMW, but this red one is another option that's high in quality, but not quite as high as the BMW, but the same economics. And so you're getting a drop in quality, but no gain in economic. So basically, there's no reason to choose the red option. And so in a binary choice, the blue and the green were equally chosen. But now when we introduce this red option, we're boosting the probability of the blue option. So the triadic choice, which we're showing here, the blue option gets chosen more often than it would in the binary choice. In fact, a lot more often. So the blue and the green were 0.5 in the binary, but now the blue is becoming much more popular when you introduce the red. And so people stop choosing the red because it's defective, but still it makes the blue option shine, and we get this attraction effect. The reason why that happens in decision field theory is that, let's say, you got the BMW, and then you got this competitor. Well, I mean, it's not a competitor, actually. It's defective. This is high quality, and then this is similar, but it's less quality, but the same economics. And so what happens is this red one, it's always going to get negative valence because it's always going to be, defective compared to the blue. And so its value is going to be driven down. So the negative valence that goes into this similar red option is going to feed back through lateral inhibition. And the lateral inhibition is a negative. So we get a negative valence from the red option feeding back through a negative lateral inhibition link. And negative times negative makes it positive. That negative lateral inhibition then boosts and adds to the BMW and boosts it up. It's kind of like the same effect that happens to perception. If you have a black dot surrounded by a white background, you get this edge enhancement effect. And that's the same kind of lateral inhibition effect that we get here. We're getting like an edge enhancement effect from lateral inhibition. So the lateral inhibition mechanism in decision field theory is important for producing the attraction effect. The attention switching mechanism is important. Focusing on attention on quality versus economic is important for the similarity effect. Now, another thing about this is that these effects are changing across time. So the similarity effect is predicted to decrease across time. The attraction effect is predicted to increase across time. Now, this is kind of interesting because the attraction effect is considered to be kind of irrational. So what we're saying is like, well, if you think harder and think longer, you're becoming more irrational because the attraction effect is getting bigger. Violations of regularity getting stronger the longer you think. And that would go against heuristic models too. Heuristic models usually say that under time pressure, you use the heuristic, and so you should show the violations more under time pressure. But when you're giving more time to think, you have more time to use a rational rule, and you should become more rational. So they would predict the opposite results. They predict more violations of regularity under time pressure, short times. Whereas the decision field theory predicts more violations of regularity at longer times because its lateral inhibition takes time to build up through this feedback loop. Then here we have the compromise effect. So this red option is like your Honda. It's your compromise option. In the green option, you can't see the blue. They're in here. That's like the BMW and the Ford. So these are the two extreme options. Now let's say in a binary choice, they're all equally chosen. But then they're all three put together, the compromise comes out looking like a compromise. In a binary, it doesn't look like a compromise. But when we put the two extreme options in there, then the red one becomes a compromise. And so when all three are present, the compromise starts to shine and it becomes chosen more often. So even though a binary choice is chosen equally often, the compromise, when all three present, and these two extremes here are chosen less often, and the compromise is chosen more often. So we produce all three effects using the same exact parameters. And the compromise effect is also predicted to increase across time. Now, we predicted these results before the experiment was done. But later on, these experiments were actually carried out, and both these findings were found. They found increases in the attraction effect and compromise effect with longer deliberation times. John Pettibone, he did the experiment and he found that these effects actually empirically occur. So those are a priori predictions of decision field theory dynamic predictions that were actually supported. Now, we've gone beyond these effects, and other people have, since our model, have developed competing models. So we, like after we proposed our model, Usher and McClellan proposed a leaky competing accumulator model that also can explain all these effects. And Bhatia proposed a associative accumulation model. These are all dynamic models, though. Jennifer Trueblood, she proposed a dynamic model. So after we proposed decision field theory to explain these effects, other models now are out there competing with us, and they can also explain these effects. So now everybody's doing research to try to compare these competing models. So that's the story so far. So anyway, that's what we're trying to show here is the advantage, though. So what we're showing is that like these economic models, these strong utility models, random utility models, they couldn't explain these effects. So the advantage of having a cognitive model, like a sequential sampling model, is not only we predict the choice probabilities, we predict the decision times and how choices change across decision times, and we can also predict these attraction, compromise, and similarity effects. These are called context effects. We can predict these context effects, which are so puzzling for the traditional economic models. And so that's the advantage of a cognitive model. And we think that's a powerful advantage and a good reason to consider the models. The cognitive models, they're more complicated than maybe, let's say, a traditional random utility model, but you get more bang for your buck too, because you get these choice probability, decision time predictions, and context effects predictions that you don't get with the traditional economic models. So I'm going to stop there and hope that you find this as interesting as I do.